Hey everyone, in the previous video I talked about using fine-tuning to teach your large language model to say I don't know instead of hallucinating. If used correctly and with a huge data set and lots of manpower, this will probably get you good results, but these results won't be very close to perfect. So let's have a bit of fun and talk about likely future developments. All of this under the constraints that LLM architecture and philosophy doesn't change, which in itself is unlikely in my opinion. For starters, let's have a quick refresher about transformer architecture. Each transformer layer has an attention sublayer, which decides which input data is to attend to. The attention sublayer itself is something similar to a neural network. While it doesn't have multiple processing layers, it does have trainable parameters, the red dots in the diagram. After the attention sublayer, there is a feed-forward neural network, and so on. All of these components comprise the transformer layer. So this is an example where small independent neural networks are kind of used within a larger architecture, and where each of these so-called neural networks has its own function. So the next step would be to keep going with this concept and expand on it. So how do we do that? Well, we have our example problem. We want hallucinations to go away, at least for the model to be able to tell us more confidently when it's sure about something and when it isn't sure. One good thing would be to have a confidence metric for the entire answer, or assigned to individual words or tokens. While LLMs can produce confidence scores for each token as it is, this isn't quite as robust, as these confidence scores are sometimes similar for tokens which are difficult to retrieve or obscure data for. And so tokens where the data is obscure in the data set, and for tokens where hallucinating happens. So it's not very useful. Looking at a model as a whole in simplified sense, if we have a feed-forward network, we have inputs on the left, we multiply them and move right towards the output. Each layer has their values multiplied by parameters to reach the next layer. Similar logic would apply to a transformer network as a whole, where you would also take into account the attention layer, normalization, etc. But essentially, as data is transformed from input to output, the data changes in concrete steps. In other words, at each step, there is a concrete value at each node, here indicated by the blue dots, and each of these values can be read at each step. Okay, so what do we do with this? Well, we train our model fully and get it ready for prime time. And now you ask the model 1,000 questions where you know it will hallucinate, and 1,000 questions where you know it will struggle, but ultimately give you the right answer. In fact, you don't have to label these in advance, as you can label them after the model gives the answer based on if it hallucinated or not. Basically, give each answer a hallucination score. Each time the model is answering, you monitor all the node values on all the layers and record them. So in essence, the meta-learning neural network will be looking at those values, the internals. You end up with a large data set where you can now associate layer activation patterns with hallucination score. All you need to do now is train your meta-learning neural network to figure out the hallucination score based on the activation patterns you recorded. Once this is trained, this neural network can monitor the main LLM and score its output on the metric you trained it on. In our case, hallucination score, by monitoring the activation patterns in real time while the answer is being generated. So it's basically just looking at all of the model internals, throw a lot of data at it and figure out what you're seeing on the inside based on what's happening on the outside, right? Sounds simple. So what are some of the downsides? And there are some. Obviously, monitoring all the nodes at once would be prohibitive in terms of memory and running costs. Your first instinct might be to monitor only the later layers of the LLM, as information from previous layers should be encoded in them. However, LLMs only encode information required to produce the next token, and this is likely not the same information we need for our metric. This means we can't have layers, nor can we have discarded values. One major goal would be thus to optimize the size of the meta-learning neural network, perhaps by having something similar to an attention mechanism, figuring out the minimal number of inputs needed to find the reliable answer, sparsity, so on. This is something that would have to be researched on a real model. And then you would have to do a cost-benefit analysis and decide how much quality you need or the amount of cost you're ready to incur to get something that is good enough. Another downside is that knowledge of certain topics is located within certain specific parts of the network. So retrieving knowledge about one subject will produce different activation patterns to retrieving knowledge about a different subject. This suggests that looking at raw positional and chronological information might not be optimal, while looking at certain characteristics such as distribution of activation values and consistency across multiple layers might be more fruitful and also less memory consuming. Since we have a large number of inputs that we don't want to discard, that is, we have no layers, and we don't know which of them are important, that means we have broad data. This is similar to genetic information, so perhaps techniques used in genetic analysis would be useful here as well, at least initially. Even something as simple as principal component analysis would probably get you going in the right direction. The initial large models can be made more efficient in subsequent iterations. And it gets very complicated very quickly, and this is where experimentation and clever testing of solutions on smaller scales comes into play. Techniques like layer-wise relevance propagation or GradCam might be interesting, but for more complex behaviors might not be enough. As you probably want real learning to happen in order to classify correctly. With regards to future-proofing, using meta-learning can be done on any future architecture and not just transformers, for as long as those architectures have a concept of nodes of any kind. The meta-learning neural network is seen as an external body which can monitor the LLM and doesn't influence its operation. You can swap it in and out as you please, integrating that into the LLM without slowing it down too much, as that would be a different engineering challenge with regards to how you access or copy out the node values in real time, meaning the internals. So regardless of how complex the meta-learning network is, the fact is that it's doable. It's a fact. However, how well it classifies the behavior you want is also up to improvement. But since we are in the business of deep learning, it's a safe bet to do something like this, just like it's a safe bet to always just add more layers. So if you're going to classify the behavior of an LLM in any way, this would probably be the best way. And by classify behavior, I mean classify the model, what the model is doing, based on observed activation patterns and known outcomes like I described earlier. So this is essentially bootstrapping, in my opinion. And just like saying throw more compute at the problem, but I don't see how we can get anything better than this without changing the architecture in a more fundamental way and moving more towards white box approaches. Personally, I believe these issues will be important enough that architectures and fundamental philosophies of LLMs and AI in general will have to evolve, so we won't have to do something like this in the future. However, it's also difficult to imagine a system that can be that can be complex enough to cover all the nuances of intelligence and at the same time be explainable. So my bet is we will be bootstrapping for the next 10 years at least. And here's an interesting bit, just as a comment. This study came out this morning, actually. Just saw it by accident. And where the authors are trying to do something similar. However, they use probes, which are very simplistic in their design and parameter count compared to the neural networks I'm talking about. They also highlight, rightly, how having the kind of access to model internals that I'm talking about, it's not trivial. It's not trivial at all. So yeah, there have been other papers thinking in the same direction, so I'm not the first exactly talking about this, but as on a level I think that it needs to be done, this is probably how it needs to be done. So thanks for watching. Drop a comment with your opinions and your thoughts.